Uh, okay, I think it's already recording. So just in case, yeah. So I posted, if you haven't seen the announcement, I posted here like a study guide for the exam, like saying which problems from the PDF you should focus on, which sections from the book it covers. I mean, if, like I had provided another reference on the Canvas site that you can find in case you don't want to pay for the, like, if you don't want to check the book because you have no access to it, you can check this other reference that I mentioned on the PDF. So, and yeah, in principle, like I thought about it, and like I don't want the exam to be too long, so I will just like the exam will only have 4 problems. Just because the thing with this probability questions is that if you know how to do the problem, it is actually quite fast. But if you get stuck and you're trying to think about the count, how it should occur, then it can actually be pretty. I mean, you can spend more time than you would expect. Mm, yeah. So all these formulas you should know. There are not that many. The only ones that you wouldn't know, the only one that you wouldn't know is like the last one, because this one I say explicitly that I would provide it. But all the other formulas, yeah, you should memorize. I mean, like really, there are not that many to memorize. So it's not too bad. But yeah, I don't see myself like giving the other one because they're kind of well, I mean, the thing is like, you mean like this combinatoric formula? Like this is like, I mean, this basic identity for n chooses R, everyone should know. These two, I mean, they're kind of more like for theoretical curiosity. I mean, most problems you can solve without knowing them. So it's not like a big thing to whether you know them or not. You should know definitely the first one on the first line, but the other two, I mean, are kind of fine to know. But I mean, if you don't know them, it wouldn't affect too much. Like I'll use none of the problems I'll give you will depend on you memorizing the last these two, but yeah, like the one for n chooses R is very useful. But yeah, like in this like yeah, this last paragraph, like the formula on this one, I would give this one you should memorize because it's relatively short. But yeah, so like the majority of the formulas on those PDF you should know. And then yeah, but as I was saying, I'll just do the exam. I'll just do it for problems because I don't want to make it too repetitive, and it's better for you to have enough time to like figure things out if you are getting stuck. The way I was going to do it is just break it into 2 parts. So like part 1, each part is 40 minutes. So for on part 1 you'll see 2 problems. On part 2 you'll see 2 problems. Basically, they will appear like kind of at like on the assignments as a quiz. Right. The probability of anything is always less or equal to 1. Right. So it doesn't matter like what you put inside of probability. So, yes, that is correct. It's always probabilities are always by definition between 0 and 1. So it doesn't matter what you have inside. You can say that the probability of any union is less or equal to 1, or any intersection or anything you want. Yeah. And then I also posted on the modules some practice exams. As I was saying, I'll try to write the solutions today. If not, definitely tomorrow morning you'll get them. And also send you the solutions for the second quiz and the quiz of today. I'll also send them to you tomorrow morning. But yeah, if you look at the practice exams and you look at the problems I recommend as the PDF, I mean, the problems on the exam will be very close to those. So, and plus check also the problems we did in class. But yeah, it won't be anything too crazy. So like if you check if those are making sense, then like you will be fine. Let's see. Let me go to the iPad. So today we have to start a useful topic. This is like probably one of the most important ideas about probability, which is called conditional probability. So it's where, like, again, like probability is a fun thing about a course like probability is that it has like many paradoxical features. Like, I mean, there are many examples that look counterintuitive, and definitely many of the examples that make probability can be kind of feel odd at a certain point is like the stuff that has to do with conditional probability. So it is useful to go slowly because it is very easy to jump to conclusions and get the wrong probabilities. So it's something where definitely you shouldn't try to rely too much on gut feeling. If we have time, we'll discuss it in the multi-hole problem. I don't know if all of you saw it, but if not, I'll just give you like a summary of what it is, because I had posted this video a while ago. But okay, so as I was saying, this is today the topic is conditional probability. And again, it's easier always to start with an example to kind of think about what the definition should be. So you roll a dice, and let's say you know that you got an even number. Let's say let's say you got an even number. Okay, so a natural question you could ask is now, what is the probability that the number you got is bigger or equal to 4? Okay. So here's how you should think about it. Well, you had, and maybe this one's relatively simple, so you could have like some idea what the answer should be ahead of already. But what you can think is like when you throw a dice, like you had like there's 6 faces, right? So there were 6 options. That you would get 1, 2, 3, 4, 5, 4, 6, right? Those are the 6 possibilities. But now you have, so if you knew nothing about, the experiment or the outcomes of the experiment, right? You can think of this as an experiment. If you knew nothing about the outcomes, the easier thing is to say that each side of the dice is like equally likely. And that's why we would say that the probability of getting a specific number was 1/6. But now you are being given some extra data, right? So it would be weird not to kind of change your expectations about what to expect, what to get, because now you have more information. So like again, if you think about probabilities as some sort of like belief or a bet that you're making that something will be true, like once you have more information, it does make sense that your expectations would change, right? That's how everyone reasons in real life. So getting an even number, right? getting an even number only make up these 6 possible outcomes kind of like reduce the number of outcomes that can actually occur, right? So getting an even number kind of like just keeps 3 of the possible outcomes, right? And now the problem was asking for you getting like a number that was 4 or equal to 5, right? Well, but it's kind of like of the possible outcomes, which are not now 2, 4, and 6, right? How many of these are greater or equal to are greater or equal to 4, like 4 and 6, right? And so what should the probability be in this case? Well, there are 2 cases out of 3 because now there are only 3 possible outcomes, right? So you have to like it does make sense to say that now there's like a 2/3 chance of getting a number greater or equal to 4, right? So 2 outcomes out of 3. So we want to say that the probability should be 2/3. Is that making sense? Any questions up to this point?
Yeah, it makes sense.
Uh, so but you want to write this in a way that is not I mean that kind of specifies that you're using extra information. So that's where the idea of like the conditional probability comes in. So what you want to say, like just like the notation that you want to say is like something like you want to say something that the probability of getting a number greater or equal to 4 given that the dice given that the dice landed on an even number should be 2/3. So like the idea like of this conditional probability notation, which is how it's written usually this way. So this is called the conditional probability. Or like let's call it probability of A conditioned on B. This just means like kind of like the probability of for A to occur given that A has occurred or you have knowledge that A is true. So it just like means like the probability for A to occur even that B has happened. Or if you want to write it in a different way, it's like your belief that A will be true given that B is now a fact. Okay. So, okay, these are great questions. So the first thing is that the first thing, like just to answer this, like it is yeah, one way to think about it in this experiment is like okay, so you were it in terms of like a frequency, if you throw this too many times, right? If you throw the dice too many times, every time the dice landed on an odd number, you kind of throw that case away. You know, imagine that you're doing this experiment a million times, and on this million times, whenever the outcome was an odd number, you kind of like don't count it, right? Like you ignore it. So now you're looking at only outcomes that were even. And so from those, that's like the equivalent of forcing the die to land on an even one. That whenever it lands on odd, you kind of do not tabulate it if you're making like an Excel spreadsheet, right? And so I'm just saying like now you would just count the remaining cases, those times where, you know, it landed on the remaining possibilities, those possibilities where it landed on something greater or equal to 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 4. And now and then and then the other question, like to answer the second question, is that it kind of, this is how you have, and this is kind of sort of point we have to go over this with some care, but you don't want to necessarily think that the events are ordered in time. And that's actually what will make this concept useful. So it doesn't matter, it won't matter which happens first. So in fact, we can compute like conditional probabilities for events that are into the future, into the past, or both at the present simultaneously. It doesn't matter, like this conditional probability is kind of independent on the of the order. I mean, this will of time, like we will see this like with more examples once we get to those cases. But yeah, it doesn't, like the ordering of the event does not matter. Is that making sense? So, yeah, it is like the wording is kind of what it can be tricky at times. So is that okay? I'm about to give you actually like a formula for how how to compute this conditional probability, but you should think about it like as a belief that you have in something occurring, given some other evidence or data that you have been provided. Okay. In fact, like before giving you the formula, let me do another example just to, because the formula kind of knowing the formula can sometimes you know screw some of these things. So let's see if I have another example here. So imagine that you have 2 coins now. So now you have 2 coins, 2 fair coins. So here's example 2. Just to make it more like pictorial, like more visceral, like more likely, just imagine one is colored red and the other is colored blue. I mean, the color, it doesn't matter too much, but it's kind of like to make it more clear that we want to think of them as different things. So you could ask, what is the probability that both, if you know, you throw both coins, right? And you don't know which, but you know that at least one of them landed on heads. So you could ask, what's the probability that both landed on heads? So you throw the coins, both coins, and you know one landed, one of them landed on heads. What is the probability that both coins actually, that both coins landed on heads? So, I mean, let me give you 2 minutes to think about it before like we start discussing it to see what do you think the probability should be. Anyone wants to make a guess? What would you say? If you had to take your chances. Good. Confusion. I like it. Perfect. You're falling for the trap. Good. So, first you have to, this is what makes it confusing. And this is like, and I'll explain why it's natural to get confused here. But here's how you should think of, here's how we want to think about the answer. So again, like that's the coloring I just said, it was useful to, okay, so yeah, okay, so here's the thing. You had one coin, one is red, the other is blue. Again, the colors is just for to make it more exciting. So what are, before knowing anything, what were all the possible outcomes? They're here, right? Here are all the possible outcomes before knowing anything. But then you have been informed that at least one of the two coins landed on heads, right? So that actually removes the last outcome. Is that making sense? And so of the three remaining, right, there's only one where both land on heads, and so that's why you would like to say that the probability is 1/3. So there's only one that actually would have the head set scenario. Is that making sense? So what is confusing is that people will say, well, this should still be 1/2 because how is it that, I thought that it's kind of should be independent, and so how can whether the other one is heads or tails is affected by what happened with the first coin, right? Like I think it's kind of how people. I mean, this is like the usual thought process of why you would say 1/2. That's probably what you had in mind, but the problem is with the wording because the wording is not saying which of the two landed on heads, right? So it's not if you had been told the red one landed on heads, then yes, I do agree. Then the probability would have been 1/2 for both to land on heads. But now you're not being told that, you know, um, which one landed on heads, and so that's what makes the difference. Is that making sense? Because if you had been told that the first one landed on heads, then you're really only looking at these two scenarios, right? And so you do have you would only have one still where it works with both heads, and so you have 1/2. But this is different because you're just being told that one of the two landed on heads. So there's a difference between those two things. Is that making sense? So like as a remark, this is different from being told that the red one landed on heads, just to give an example. And this is where like the wording gets tricky, and this is like I mean you can already see this like having applications to genetics, because in genetics what like they're dominant and recessive genes, that's how it's called, like for certain traits. I don't remember like what is a dominant or recessive thing, but you could be told like, yeah, you have like two individuals, and one has the dominant version of the gene, so you could be asked, well, what's the probability that the second like the both of these two individuals have the dominant version of the gene? And then you could just go with 1/2. You have to be careful of the wording because it depends on whether you know are you specifying which individual has a dominant or not. So it is like that's what's affecting the overall calculation of the probability. So this is like what is so just to like how we would write this, like just to start getting used to this terminology of condition. I don't know why this like ruler appeared out of nowhere. So just to get used to I should have written this in a let me see if I can move this to a different paper, because because this is for exam 2, so I don't want it to interfere. So just give me a second to try to export this. I forgot about that. Let me call part 2. I don't want to confuse things, so let me see if I can copy paste this. Just give me a second. Okay, I need to zoom out. I'll just copy this one first. Perfect. And if I don't copy it right now, then it will become a mess. So just give me it. Yeah, because I only written 3 pages so far. So I better do this now. Copy. And then this is good. And just one more. Also, I mean, the last one. I really like this notability app. If people haven't, if you have the like a tablet with Apple, like it's a good app to have very convenient. So okay, now we're back on track. So yeah, like what I was saying is that in the notation that we want to use, what we would like to say that the probability of two heads given, like this vertical bar is read as given or interpreted as, given that one is a head, one landed on head, is 1/3. Okay. But this is a good example because, like, it doesn't matter. Like, you could have thought that both coins were thrown at the same time, but you could also have imagined that one was thrown and then 2 minutes later the other was thrown. Like, here there's no temporal. The events are not happening in a specific order. Is that making sense? So it is not the time plays no role in this conditional probability. So here, like, so as a remark in general, for something like this, for these things, it doesn't matter whether B or A happen first, etc. Or one earlier than the other, etc. No, that's different. That's not what I'm saying. No, actually, it won't be the same. The Bayes theorem will allow us to relate the two. I'm just saying that this does not assume that B is before A. This does not mean that B happened before A. That's what I'm trying to say. But yeah, no. Actually, a good question is to ask whether this is the same as PVA, and that's not the same. So, like, here's one more clear example. And this is actually how you make inferences about the past, right? Like, so you could ask, well, what's the probability for dinosaurs having existed, right? Given that we have fossils, like we have found fossils. Right, these, like, if you write it this way, well, having found fossils or remnants, it is something that's happening in the present, right? And then you're asking about something that would have been in the past. That should be different. I mean, or there's no reason for that to be the same as, like, the probability that there would be fossils for dinosaurs, given that there were dinosaurs in the past, right? And so should be different. Or there's no reason for it to be the same. Doesn't have to be the same as. Is that making sense? So both probabilities could be computed in principle, but they do not they do not need to agree. In fact, like in the we can make it even more extreme because we can do it for this case, right? Like what would have been like going back to the previous example, going back to the previous example where we do have like the probabilities. If you flip these two factors, right? What's the probability that one landed on head given that both landed on head? And the answer should be easy. Yeah, if you know that both coins landed on heads, you're certain that at least one landed on heads. That making sense? So this is a good example because it completely changes from 1/3 to 1, right? Like so the values can like radically differ. Does that make sense? So now we can get to this. What is this? What is this formula? What is this formula for the probability supposed to be? This conditional probability. I still haven't given you that formula, but maybe before that, what do you think? Just as a more conceptual question, because this will be useful for us in a moment. What should you think is a probability? What should this be equal to for any experiment, for any proposition? Like, what should be the probability of B given B? More or less an just one, yeah, because it's kind of like, what are the chances that B is true given that B is true, right? It's kind of circular. It becomes like almost like a tautology, right? So this one should be 1. And you can think of it as some sort of like we'll think about this as a normalization factor in a second. So like it's almost like a normalization means usually when something is forced to be 1 or like when something gets rescaled to a particular value. And that's kind of useful to keep in mind because it will suggest what the formula for the conditional probability should be. So what's this formula for the conditional probability? Well, it is useful to think of in these pictorial terms of a diagram. So if you had like two, again, these A and B refer to statements or propositions or outcomes of experiments. So maybe you have here like a diagram that represents the possible outcomes of A. And here you have a diagram. In this same diagram, you have some, this portion represents the possible outcomes for B, right? So the idea of like having the conditional probability, right, is that, well, you should only pay attention now to the region in the space or the diagram where B is known to occur, right? So kind of B becomes like true for sure, right? So everything that takes place would take place already inside the region determined by B. So like what it seems like, I mean, what you will look at, then it's kind of like what A and B have in common. If you notice, like that's kind of what we have been doing in the previous examples. You will look at A and B have in common. And so the formula for the conditional probability should be the probability of A intersection B, right? But this cannot be quite the final answer, right? Because we want to get, like, we should, we want this to work, right? So what would be the easiest thing to make a formula like this work, to fix this formula, so that, like, if you put B here, you get 1. Yeah, exactly. So and what here counts as area would be probability. So that's a normalization or rescaling that you have to use. And also it's good because that introduces the asymmetry between this A given B versus B given A, because now B appears both in the numerator and the denominator, right? So that will make it different from the other possibility. Okay, and this is like the formula for the conditional probability. Is that making sense? Is that okay? So far, so good.
No problem.
Now, and that already, oh, I should say, it may have been implicit, but it's not a big thing here, but like that's obviously this formula you would only define to start with when the probability of B is bigger than 0 to begin with, right? So implicitly assumes. Which in practice, like especially the stage in which we are on this course, like that's totally fine, because if something has probability 0, we are interpreting that as being impossible. So there's no point in trying to condition an event on something that won't happen. You know what I mean? So it is like a restriction, but it's like a very small restriction to make, because again, in practice, like you only want to take conditional probabilities when B has a chance of occurring. Is that making sense? So it's like, it's something that needs to be mentioned, but it doesn't, like, make a big, especially at this point, like it doesn't make a big mess of anything. And what do you think? And now you can just use this formula and reverse the roles of A and B, and then you would get like a formula for like the opposite probability, right? That B, the probability for B to be true, given that A is true, or that A. Well, and if you look at the formula, you get probability of A divided by B divided by the probability of A, right? That should be what you get just by switching the roles. And you get to one of the most famous formulas in all probability, which is the Bayes theorem or Bayes formula. Well, what did these two formulas have in common? They share this numerator, right? This numerator is the same. If you divide, I mean, you can write it in different ways, but you could start by dividing these two equations. And again, when I write this, like I'm already implicitly assuming that the probability of A is positive. We're just in these cases which are interesting. And just some basic algebra. This is this. And you can solve for one of them. So let's just solve for the probability of A given B. And you get to the Bayes theorem. Bayes was a name of a reverend mathematician, I think, Catholic priest who was studying genetics or something like that. So he found this result. This is where Bayesian analysis comes from. If you have ever heard that word, that's very popular terminology in statistics and data science and all that stuff. Okay. And this is like, is that okay? Let me stop. Is that making sense so far? So good. Are there any questions about this? And this formula is really, really, really useful. Like way more useful than you would like ever even credit for. It can like there are some problems of conditional probability that really you would have no way to. There will be no way to even try to start it if you didn't have like this formula like accessible to you. So it is one of the most fundamental formulas of all the entire course in probability. Like, and then so yeah, it is really, 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 really important. Almost everything like that involves conditional probability uses Bayes theorem in some form. Is that making sense? I guess I'm about to do some examples with this, but I just wanted to see if there were any questions up to this point. Okay, so let's take just like a quick 5-minute break. Because it's a good place to stop temporarily. So once we return, I'll just show you some examples of how you can use it. Okay, and these problems are really fun. This is one of the most fun parts of the course, I feel, like this conditional probability. And we can discuss the multi-hole problem as well. So we'll do that in 5 minutes.
Professor, just had a quick question as well.
Yeah.
Review one of the questions that were assigned for like the quiz today. Do you think we'll have time for that?
Well, yeah, but let's see. Like you can stay after like I'll officially end it. And then you can ask after I officially end the class, you can ask me about that, and then you just take the quiz at a slightly later time. Yeah.
That's good.
It sounds good. Okay, let's just take a 5-minute break and we'll. Okay, so I only wanted to do 2 more examples, but before we do them, so we need the Bayes formula, and there's something else that we need, which is called sometimes called the law of total probability. So here's what. I mean, again, it's kind of one of many of these things in probability. You just use like make an observation that looks very, very silly, and then you kind of get something very, very useful. So for that, it's kind of convenient to draw the diagram again. Kind of like a picture is more useful than anything else you could make. Maybe you have probability of A, even probability of B. So let's say you started with a probability of A. So notice that this is not a conditional probability. It is just like the ordinary probability of A. Okay, so that should be like what I'm going to claim is that this is the same as the conditional probability of A given B or B complement. So just to remind you what this means, like B union B complement means that like corresponds to B or not B, right? So this like is kind of like B or not B, right? So this is saying kind of like it's better to think about it like intuitively. Like it's what's your belief that A is true given that something occurred, right? But that something is like totally non-specific because this something would be like, well, the coin landed on tails or the coin landed on heads, or the dice landed on 6 or the dice landed on something not being equal to 6. You see, like B or not B is like this was a tautology, right? So what I'm saying is that your like the probability cannot change because of that. Is that making sense? Because you're not saying anything. You're just saying something occurred, but like the way you're saying that is completely unspecific. You're just giving me like the list of all the things that could have occurred. Is that making sense? Everyone is convinced of that.
Just wanted to ask something to clarify. This is like the probability of A given B or not B, right?
Right. This is like the probability of A given B or not B. Yes.
Gotcha, gotcha. Okay, I just wasn't sure if like the A given B was separate from the other part. But
Oh no. Okay. Okay. I get you. Get you. Like could be confusing in terms of notation. Like yes. Like the like the vertical lines are affecting all the expression here.
I see.
Yeah, it can look a little bit ugly, but right. If to make it super precise, yeah. It would like strictly speaking, like it couldn't have been this or something like that because that wouldn't make a lot of sense because this is like a number, right? And this is like a set or like an event or a statement, so you cannot really combine them. But yeah, like it's just to make it, since this is like the first time, it's also especially useful to to kind of like put the parentheses if that makes the notation more clear. But yeah, that's what I meant. Yeah. But yeah, so it's kind of saying like your belief that A will occur. I mean, it's unaffected by knowing that a tautology is true, right? It's kind of like saying what's the probability that it will rain tomorrow given that 2 equals 2. Like it doesn't make a lot of not so clear how that should affect your probability computations because 2 was always 2 to begin with, or 2 is equal it's kind of like, yeah, it's not. So whenever you condition on like when I'm trying to say the probability of A should be the same as the probability of A condition on any tautology. That's essentially what I'm trying to say. Okay, and again, this is very silly, but it's kind of useful because if you look at the formula for conditional probability, that should be the probability of A intersection. Okay, now the parentheses here are actually useful. So given this, and then there's this thing. Okay, first, what should be the denominator? The probability of the denominator should just be 1, right? Because that's B or not B is a tautology. And then there's like these things which are called the De Morgan's laws, which you can find on the book, but you don't have to know that. But I just will give you what this means. Like, it's kind of asking how can A, in terms of a picture, you have B and the complement, and so like this intersection is how do you split A among these two pieces? Well, you can look at the piece of A that's inside of B, or the piece of A that's outside of B, and those are the only two things that can occur. Okay. Is that making sense? Because it's kind of like saying like here, this is looking at the stuff of A, which is shared with B or not B. Or that's like the stuff that A shares with B, or the stuff that A shares with not B. So you kind of can break like I mean, again, like I'm not going to make this. You don't need to know these properties about set theory, but it's kind of like natural way to break A among the two pieces. It's kind of saying like that the A is equal to this piece inside of B and this piece outside of B. That's essentially all that it's saying. So it's kind of like you're breaking A into the stuff that's landed inside of B and the stuff that landed outside of B. But I don't know if anyone can notice, what's the property between these two regions of different colors? How can you find, there was a formula for the probability of a union, right? Think of this as union of two things. So what's the formula for the probability of a union?
Plus.
Yeah, it becomes a plus. In principle, there will be minus the intersection, but there is disjoint or mutually exclusive. So this is just the probability of A union B plus the probability of probability of A intersection B plus the probability of A intersection B complement. Okay. Okay, and then what? The probability of A intersection B, you could leave it as that, but it is more useful to go back to the formula of conditional probability and notice that that formula allows you to solve for the probability of the intersection. So you can say that the probability of the intersection is a probability of A given B times the probability of B. So if you use the formula for conditional probability, you get the probability of A given B times the probability of B plus probability of A given B complement given the probability of B complement. Okay, so let me, again, this kind of wasn't like a derivation to motivate the formula, but like you can just remember the formula. So this is called the law of total probability. It says that the probability of A is the probability of A given B, given the probability of B, or the probability of A given B complement, given the probability of B complement. Is that making sense? And okay, again, it just requires some examples to see all of this play out in practice. So let's do some examples about the uses like the base formula and this law of total probability so that you can actually see concrete things that are interesting to have. So let me do an example illustrating these two formulas. So here's an example. Let's start with one. There's actually one on the PDF. So this is problem 18 on the PDF of problems. So you have one third coin and one bias coin. that lands on head with probability 3/4. Okay, so the question is, you choose one of these two coins. And flip it 3 times. And obtain heads every single time. What are the chances? Here's the question. What are the chances that you pick the third coin? Okay, so just to explain the problem, so you have 2 coins. One is fair, the other is biased. You choose one of the two. You don't know which one you chose, but you notice that when you flip the one that you chose 3 times, you always got heads. So what you're asking is, what is the probability that you chose the fair coin, given that you got 3 heads, 3 consecutive heads? Okay. Is the problem making sense? The wording of the problem. So let's try to find this out. And again, like you'll see, it is kind of subtle, and you have to like kind of like setting it up just helps a long way in and getting the right answer, even choosing the right words for like the propositions or the outcomes. So F would be the statement that you pick the fair coin. And let's call A the statement that the coin you chose lands on heads 3 times. Okay. So what are we after? We want the probability of F given A. So we want to know the probability, the chances that we got that we had chosen the fair coin, given that we know that for the coin that we chose, that coin landed 3 times. Is that making sense? So far, so good. How we're gearing towards a solution. And here's the thing, this problem is complicated, and the miracle of the base formula is that you can't change it for something that's way more tractable. So again, the idea of the base formula is to flip the order on which the terms in the conditional probability appears. So if you use the base formula, according to the base formula, you can flip the factors, right? But when you flip the factors, you have to multiply by the probability of F and divide by the probability of A. I think that's yeah, that's a correct. Is that making sense? So the idea is that actually each of these will be way easier to compute than the original one. So we can start with each factor one at a time. So what do you think? Let's start with the first one with let me put it in blue. So what is P of A given F? That's the probability of getting three heads, right? Given that your coin is fair. Okay, so this is a probability you should know how to do. What is the probability equal to?
1/8.
It's 1/8, right? Because the fair coin, like, you know, when you throw it 3 times, there are 2 to the 3 events, right? So there are 8 possibilities. So it's, and only in one of them, all of them happen to be 3 heads. So it's 1 over 2 to the 3. So it's 1/8. Is that making sense? So this is like the flipped conditional probability. Notice that it's a lot easier than the other one. Now, are there any questions about this one? Let me use a different color. Okay, now here's the second question. What's the probability of having chosen the fair, that you chose the fair coin?
1/2.
Yeah, because it's kind of like, well, you have 2 coins and you're like a random, like, you know, blindfolded or whatever you want to think about it. You just grab one. Since you don't know any other like conditions about the problem, you just have to play it fair and say that it's 1/2 because there were only two choices to choose from. So this is sometimes called the this is a terminology you'll see many times in statistics. This is sometimes called the prior probability. Because this is like the probability prior to having done the experiment and knowing that you got three heads, right? So before knowing anything about what outcomes you're getting, you know, what were your chances for like having chosen the fair coin? Well, it was just 1/2 because you know you have no other data. So it's kind of like sometimes it's called prior in the sense that it's like probability before like collecting data. Okay, and this one it should is called sometimes the posterior probability. Because it's kind of like the probability that you have post the fact, after you have information, the information being that the coin landed 3 times on heads. So this is why, and this is kind of like how these machine learning algorithms, all of these things work. When you maybe start with the prior probability that you feed into the machine for like, you know, expecting like, you know, for identifying cat images or whatever, you feed it like some you have like some prior probabilities and then you run like an algorithm or something like that, the machine learning algorithm, and that corrects for those probabilities or And maybe we have time. We'll see if we should talk about how those things work in practice. But I mean, I'm just saying, like, there's like a difference between the probability before knowing and after knowing. Because like the evidence should play a role in your expectations about what is true or not. Okay, that's kind of reasonable. Okay, and then here comes the last part of the problem, which is the probability of A. So that's the probability of getting 3 heads. But then you say, okay, this is confusing because, you know, like that the answer kind of like the probability for getting 3 heads actually depends on whether you chose the fair coin or not. And this is where actually you have to use the law of total probability. So again, like it kind of just found that like if you just write it like that, there's some way to compute this. But if you use the law of total probability, the problem becomes really, really easy. It becomes the if you use the law of total probability, this is the probability of A. So we're going to find the probability of A, given that you chose the fair coin, times the probability of F, plus the probability of A, given that you didn't choose the fair coin, times the probability of not choosing the fair coin. Right, because like the idea of like the law of total probability is that you can split the probability in terms of a sum of conditional probabilities. If you condition, if you use like an event, you see, like I'm just taking F instead of B in this formula. So you like it's basically you're saying I'm going to compute the probability, kind of assuming first that you had chosen the fair coin, and then assuming that you had chosen the bias coin, and see what I get. And the probabilities just add up more or less. That's essentially what the law of total probability says. Is that making sense? So what is the probability of choosing the fair coin? Well, we had said it before, it's just 1/2. And this one is 1/2. Right, because the complement of being fair is like the other one, which is the bias coin. So if the fair coin had a 50% chance of being chosen, the other one has like a 50% chance of being chosen. And now here comes actually we computed this one before, right? What is the probability? Oops, that's kind of fun because this appears also in a previous calculation. What was the probability of getting 3 heads given that your coin is fair? We actually have found that before. So this is like 1/8. So we already had this one. And now, so we are only left with the probability of getting 3 heads given for the bias coin. So what should that probability be if you know that the probability of the bias coin for getting a head is 3/4? So what would you put here?
It's just like 3/4 in parentheses to the third power.
Right, it's like every time the bias every time for getting a catch, the bias coin has a chance of 3/4. So in three throws, flips, it would get 3/4 cube. Perfect. But notice that again, each of these factors will become a lot easier to compute. And so yeah, let's see. So okay, like you can simplify this again if you want. This is 1/8 plus what is 3/4? 3 cubed is 27, right? Over 4 cubed is what, 64 over 2. Okay, so let's see. Let's be lazy and write it on Wolfram Alpha. This is where I'm saying like, oh, it's nice to have a calculator. It's 35 over 128. And now we're ready to put everything back in place. So again, the probability because of the base formula, going back here. Was this, but what was the blue term? The blue term was 1/8. The red term was 1/2. And this term was 35 over 128. Again, I mean, you could leave the answer like that, but it's nicer to put it. You get 835. Which is about 0.23. Oh, thanks. I was cheating on Wolfram Alpha. So I didn't check the chat. So it's a little bit less than 20, almost 20. I mean, a little bit less than 25% that the coin that you chose was a fair one, which makes sense because the bias coin had like a 75% chance of like, of landing on head. So you would expect that to be the more likely thing if you got 3 times heads. Is that making sense? But it is like a very cool example because it just shows you the power of this conditional probability. And again, like you could imagine it for medicine or biology or all these other places where like it just has many ramifications, because in almost every study about nutrition or whatever, you have, you will get probabilities conditioned on certain facts or things you have discovered, right? I mean, this is like a concept that is almost impossible to get away from. So it's a nice way to see like work. Is that okay? Are there any questions before? I think it's a good place to start wrapping this up, today's class, because I want to post that you work on the quiz. So are there any questions about this? Okay, so I'll make the quiz available now in case anyone wants to take it. I mean, I'm also, yeah, if you want also to, so yeah, you can now take it if you want. I'm also can answer a question or two if someone wants to ask me before they take the quiz.
Problem 34. I just wanted to figure out how to do the last two on that one.
Oh, yeah. So for the probabilities, yeah, I actually had written it before during office hours, but I already erased it. But the idea is like, for the probability of the balls being different, I can write it on the chat on the iPad so that it remains for future references. This is still the video. So is this like one of red, blue, green? Let's see. Let me just share the iPad. Okay, so let's see. Yeah, let me put this question 34. Question 34. So for C, right? you have 3 different colors. So you have 4 reds, 8 blues, right? And you have 5 greens. So like the easiest thing is just to think first, well, what if I want the last 3 to be of different colors, right? So just think first that you want them to appear in a specific order, right? So let's say you want them to appear red, blue, green. Like in how many ways could this happen if they appear in the order red, blue, green? Well, you get 4 slots times 8 times 5. Is that making sense? If you specify the color in which the order in which the colors appears.
Mhm.
Is that okay? Is that reasonable? So that's the total number of options where you would have those configurations. But the probability would be divided by like just like have like all the possibilities, which is where like you're not making distinctions about the colors. So how many balls do you have? You have 17 balls, right? So it would be times 7 divided by 17 times 16 times 15, right? So that would have been the probability. Is that okay? Up to this point. Or is that making sense or no?
Sounds good.
But now you were not asked to do this in a specific color, right? Ordering. So you just have to ask, well, how many ways are there to permute the colors around, right?
3
Because you were not
factorial.
right, 3 factorial, because you were not asked that it should appear as red, blue, green. So there are like 3 factorial ways to permute the colors, to reorder the colors. So the probability is just that one times 6. Is that okay? Is that making sense or
Yeah, that kind of makes sense.
and then yeah, it's just like and then for part D, do you have the book, by the way, or you do not?
I haven't pulled up, if that's what you're asking.
Yeah, I'm just saying because like some of this I did take from the book. This is what problem like 218 on the book on the self-test problems. I like those because they have the solutions written at the end. So
I
it's
see.
always yeah, it's nice to check. I mean, not all of the PDF are from the book, but at least like a half of them are from there. And then okay, so now you have then the part D was like the probability that the 4 balls are consecutive, right?
Mhm.
So again, like you kind of have to ask like, well, what are the chances? That means that how many scenarios like can you put? How many combinations of the 4 red balls can you do? You can do like 4 times 3 times 2 times 1. That's how you can rearrange the four balls, right? Divided by all the number of balls. There were 17 balls. So that would be like the probability of having just 4 balls together. But then like you have to be like, well, they can be placed like, you have to arrange them like all in a line. So you have to just check where can you put all, like, think of the 4 balls as kind of like a chain like the 4 balls are connected by some sort of chain. So you have to decide where do you put like the chain, right? So you have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 spots. So you have to check where could the chain start. Oh, the chain could begin here. It could also begin here. I mean, it could always begin. It can almost begin on any slot.
I see.
This is the last slot where it begin, except the last 3, right? Because in the last 3, you could not place the chain. Like, you would need
Yeah.
one more room. So there are 14 places where you can begin the chain, and so that's why you multiply by 14.
That
Oh yeah,
makes
you
sense.
can leave. Sorry, you could leave if you want to take the quiz now. Sorry about that. For the question in the chat, yeah. So 14 slots to place it.
And you just multiply by 14, right? Not
Right, you just multiply by 14.
I see. Okay, that makes sense actually. I saw that explanation online as well. That one. That made sense to me.
Okay. By the way, let me stop. Okay, is
Uh,
that
I just want to add, I think there's a typo in question 32, like the answer.
Oh yeah. All right. That there's like an extra 0 missing.
Yeah,
Is that what that was on B and C, right? Or just B?
yeah, B and C.
Yeah, no,
It's
thanks.
supposed to be
I
3.0.
right, no, thanks. Yeah, I think someone told me earlier, and I'll fix it on the PDF, and I'll post like a new version for the solutions. But thanks, yeah.
Okay,
Thanks about that.
no problem.